Hello, my dear students. Welcome to today's class. So, in yesterday's class, I have started the chapter BGT biasing, where we have seen what is biasing and also need for biasing we have seen, and also for common emitter configuration we have seen the construction for DC load line. We have seen the definition for DC load line. After the DC load line, we moved to the Q point, wherein we got the expressions for the coordinates of the Q point. Okay, so that was about the common emitter configuration. For the Q point, I just want to solve one question that is from the what we can say expressions what we have derived for the Q point. The expressions for that I'll be using the circuit, the similar circuit what we have used in yesterday's class. I am solving the problem. After that, I will move to the next topic. Phase emitter. This was yesterday's circuit. The two values will be given. We have to solve for the given values of RC and BCC. So the value for RC and also the value for beta is given here. For this particular transistor, the beta value is given as 200. This is 1 kilo ohm and this is 10 volts. Okay. So we have to solve for the Q point coordinates. This is V1, otherwise this is VBB, this is BCC. Okay. So we have to solve for the Q points. The three values of IB are given here, where IC is equal to, we have the expression for IC. ICQ is equal to beta times of IB. The two expressions for the coordinate, the first coordinate ICQ and the next VCEQ is VCC minus ICQ RC. That means whatever value for ICQ we will get from this expression, we will substitute here and we will get the ICQ for given value of IB. Okay. Here 200 beta value is given, the different values of IB are given. This particular question is to compare the Q points, okay, for different values of IB. And the values of IB are given as 10 microampere, 20 microampere and 40 microampere. So you have to solve for three coordinates of the Q points, right? So we have the expressions here. We have to substitute the values and we have to find the value for ICQ and VCQ for given values of IB. Okay. So the first one I am going to solve now. ICQ1, which is beta times of IB1, I can say. I will say this is IB1, this is 2 and this is IB3. Okay. So 200, what is the first value? Microampere. So ICQ1 is nothing but 2000 microampere, that is nothing but 2 milliampere. So for the value for first ICQ is 2 milliampere. The next we want is VCEQ1. So here we will substitute the value what we have got as ICQ1. We will substitute in this particular expression. Okay, VCC minus ICQ1 RC. Okay. So what is the value of VCC? 10 volts minus what we have to do now? 2 milli into 1 K. Milli and K gets cancelled. So what you are going to get here is 8 volts. 10 minus 2, 8 volts. So this is the first. These are the first coordinates for the what we can say, Q point. Okay, so this is the first Q point. We can say it as Q1, and that is given by 2 milliampere. Otherwise, along the y-axis first, 8 volts, 2 milliampere. This is the first coordinates. We'll find the second coordinate we require and also require the third coordinate. For that, we will be solving using the same expression. Now, ICQ2 is equal to beta times of IB2. That is 200 into 20 micro. Okay, 200 into 20. Oh, sorry, it is 25. Doesn't matter. We can also do it with 20 also. Okay, so 25. But what is given here is 25. It's okay if we do with the value is 20 also. Okay, so this is nothing but 50 and these 200 microampere, which will give you what? 5 milliampere. So ICQ2 is 5 milliampere. Now we will substitute that in this expression to find BCEQ2. BCC minus ICQ2 into RC. 10 minus 5 milli into 1K. Okay. So 10 minus 5 is equal to 5 volts. So the next coordinate is 5 volts, 5 milliamperes. Q point 2. Next, we will find ICQ. From the single expression for ICQ and VCQ, this same expression is used for different values of IB, and depending on that, we are finding different coordinates for the different 3 Q points. When we are going to get 3 different values for IB, we will get 3 Q points, separate Q points. So now, what will happen here? Beta, that means 200 into what is the next value? 40 microampere. So what it will be? 8,000 microampere is equal to 8 milliampere. BC3, this is BCEQ3 is equal to BCC minus ICQ3 into RC. This can be written as 10 minus 8 milli into 1K. This will give you 2 volts. So the next coordinates are 8, 2 volts, 8 milliamperes. Okay, so these are the 3 different Q points we are going to get here. Now we are going to plot it on the graph. Graph of the output characteristics of a transistor. So it is VCE versus IC in terms of milliamperes. This is in terms of volts. Starting with 0, I will take steps of 2, 4, 6 and 8. 2, 4, 6 and 8. Of course, milliampere and volts. Okay. So the first value is for 8 volts. We are getting 2 milliamperes. Okay. So here we are going to get a point. Here we will get a point. This is the first point. Okay. Next, 5 and 5. That means between 4 and 6. So we will get somewhere here. Okay. This is the second point. So this is Q1. This is Q3. Okay. The next one for 2 volts, 8 milliamperes. This is the point. Okay. So these are the 3 possible Q points which we are going to join now. Okay. Now if we join these lines, these points, we will get the load line. Okay. So these are the 3 Q points. This is Q3. Okay. And we can observe that Q2 is exactly at the middle of the, what we can say, load line. Now this is load line, and Q2 we will find to be at the center of the load line. So if we are going to select the Q point for amplification purpose, then this will be the ideal Q point for the amplification purpose. Okay, so how the characteristics will appear now? This is the cutoff region. This is the first value for first ID, otherwise the Q1. The next curve will pass through this Q2. The next curve will pass through Q3, and the other will be falling here. So this is the characteristics. And for this particular problem, where we have taken 3 different values of IP for different values of IP, this is for 10 microampere, this is for 25 microampere, this is for 40 microampere. We are going to get such graph where we are going to get 3 Q points, Q1, Q2 and Q3, where we find that Q1 is nearer to the cutoff point, and Q3 is nearer to the saturation point, whereas Q1 is exactly at the middle, 5 and 5 milliampere and 5 volts. That is also what I have told in the previous class, that if we want the Q point to be at the middle, the VCE value has to be half the VCC. That means the 5 volts, right? This one. So that is the best suitable Q point for the purpose of transistor as an amplifier. Okay, so this is the problem that I have taken for the different values of IP, finding 3 different coordinates for the Q points, Q1, Q2, Q3, plotting them on the graph, output characteristics of a transistor. Okay. Next, I will move with the next topic, which is very important, called as the voltage divider bias, otherwise potential divider bias. This you have heard in the yesterday's class, where you have seen the different types of biasing methods, where I have told the biasing methods are base bias, otherwise the fixed bias, emitter feedback, otherwise emitter bias, collector to base bias, and the last one, what I have listed in yesterday's different method of biasing, is the voltage divider, otherwise the potential divider bias. So I will move in further with that thing now. That is the voltage divider bias. So about the voltage divider bias, I would like to say that it is the most widely used type of the bias. There are certain reasons for it being the most widely used that you will come to know when you are going to study in detail about the voltage divider bias. When we are going to find the different parameters, otherwise the end points of the load line for a voltage divider bias, when we are going to analyze the circuit for the voltage divider bias, then you will come to know why this is widely used method of biasing in the transistors. So for now, you have to know that it is the most widely used method of biasing. Okay. So I am moving now further with the voltage divider bias. Yes, so the voltage divider bias. So one thing you know now that it is the most widely used method of biasing a transistor, the voltage divider bias. I will start with drawing the circuit for the voltage divider bias. Of course, it requires a transistor and we are using a NPN type of transistor. The circuit will be having a network that shows you the concept of use of two resistors that are connected in the form of division of the voltage, so that they will divide the voltage. The two resistors are used are R1 and R2. The two resistors are used R1 and R2 for biasing a transistor. A resistor is across the collector terminal termed as RC. A resistor is also present at the emitter terminal termed as RE. This is RE. Okay. From this IE flows. We are applying a voltage VCC here. IC flows. IB is here. I1, I2, where we can say I2 is equal to I1 or I1 is equal to I2. This is R1 and R2. Because of the usage of two resistors for biasing the base terminal of the transistor, this particular method, otherwise this particular setup of the what is the circuit is called as voltage divider circuit. Okay. The voltage across the R2 is termed as V2. Okay. Where R2 is nothing but V2 is nothing but R2 into I2. Okay. The voltage across R2 is V1. R1 is V1. Okay. Plus VCC here. IE, RE. This is the ground terminal. Okay. Here we will come across, this is collector, this is the base, this is emitter terminal. Okay. The voltage across the collector to emitter is termed as VCE. This is VC, voltage across collector resistor, that is VC is equal to IC into RC. This is VE, that is nothing but IE into RE. Okay? Right. I1 is equal to I2. Here also we are getting three voltages, and for this particular loop we are having three voltages. Here we are having three voltages. V2 is one voltage and another voltage is across the base to emitter, that is called as VDE. This portion is called as, the voltage is called as, the voltage across the terminals base and emitter is termed as VDE. And here again VE is applicable to output loop as well as input loop. Okay. So this is the circuit for voltage divider bias, where we can see two portions. This is the input portion of the circuit, that is to the base terminal. Here in the analysis of this particular circuit, we will be considering two loops, wherein one is applicable for the base terminal and another part is applicable for the collector terminal. Towards the collector terminal, we are having total three voltages, VC, VCE, IE. Okay, that is drop. There are three drops resulting from VCC. Okay, and here we can see that there is V2, VD, and VE applicable to only this loop, not the upper loop. Okay, right. So this is the circuit. This is called as voltage divider bias. Why voltage divider bias? Because portion of the voltage, that is V2, is biasing the terminal base. Okay, so that's why it is called as voltage divider bias, right? Will be using two different loops for the analysis: base loop and the collector, that is the output part and the input part of the loop we'll be using for the analysis. This R1 and R2 are responsible for biasing the circuit. This RE for maintaining the stability in the circuit. Okay. Excess current will be passed through the ground by this RE. Okay. So that's why this RE is meant for stability, for maintaining the circuit stable. The what we can say operation of this RE. Okay. So now we will start with the analysis for the circuit. We are considering two parts. This is the base part. I will start writing from here itself. So now we are going to derive the expression for what? Two terms, that is IC, the same because we require IC saturation point and the VCE cutoff point. 2 points we require, the two end points of the DC load line are required to draw the DC load line. That's why we are focusing on the two parameters. One is the IC and the other one is the VCE. Okay. So for that, I will start from this loop where I am applying KVL. Okay. We are applying KVL here. Right. KVL to base loop. Otherwise, you can just name it as L1 and you can write L1. So here what we can write here is V2. Before that, I am going to write the expression for VCC. Here, I will show it in terms of another circuit here, where we can see that it is applied like this. The two resistors are connected like this. We are ignoring the collector portion here, so we can just see that this VCC is applied like this plus VCC. So the total voltage will be V1 and V2. Okay. So what we can see here is total VCC is V1 plus V2. First we will write this one. Right. So we can write VCC is equal to V1 plus V2, where it can be further written as V1 is equal to I1 R1 plus I2 R2. What I have written in the expression that I1 is equal to I2, so we can write it as VCC is equal to I2 taking common R1 plus R2. Okay, so I2 can be written as VCC by R1 plus R2. This expression you can directly get from the voltage divider rule. Okay, that also I will tell you. So what is V2? V2 is equal to I2 into R2. So VCC by R1 plus R2 into R2. This is nothing but the voltage divider rule. Okay? Nothing but the voltage divider rule. Right? So now we will apply the KVL to the base loop, where we can write the input voltage is V2. That means the voltage drop across the R2 is the input. So we can write it as V2 is equal to VBE plus REIE or IERE. Okay. This particular loop, input voltage is voltage drop across R2. That is nothing but V2. Input applied to this particular loop is voltage drop across R2, that is nothing but V2. That will split into two parts, that is VBE plus IE RE. That means VE, that is nothing but VE. We can first write VE and then also we can split it, make it as IE RE. So we can write it as VE also, right? So what will be V2 now? V2 is equal to VBE plus IE RE. Then we have derived the expression for V2. I will write the expression for IE now. I am rearranging this particular expression for IE. This particular expression I am rearranging for IE. So what happens if we are keeping the IE RE at this side only? It will be VB will move that side, so it will be written as V2 minus VBE. V2 minus VBE. The term with IE is RE, that will come in the denominator. So this is the expression, and also IC is approximately equal to IE. So we can write as IC. So we got the expression for IC, where IC is equal to V2 minus VBE by RE. So this is the expression for IC. Okay, the expression for IC is for the base part. The expression for IC. This is from the expression IC is equal to IB plus IE, because IB is a very small quantity of current. That's why we can directly write IC is equal to IE. Here also I forgot to mention that point, that IB is very small amount of current. That's why IE is directly considered that is equal to IB, because we are neglecting the value of IB. That's why IE is becoming equal to I2 in this case, right? So totally the IB value is very less. That's why we are not considering in the calculations. Okay. So this is about the IC at this point. Now we will move to the collector part, otherwise the output part of the circuit. Okay, so the expression for IC is equal to V2 minus VBE by RE, where V2 is VCC by R1, R2 into R2. Okay, VCC into R2 by R1 plus R2. That expression you can also get directly from the voltage divider rule. So we got the expression for IC. Now we have to find the expression for VCE. Now we will consider the output loop. Now we are going to consider what? The output loop. Now moving to the output loop, otherwise the collector loop. Apply KVL to output loop. So what will we get now? This voltage VCC is equal to this plus this plus this. Okay. VCC is equal to VC plus VCE plus VE. This can be further written as VCE is equal to VCC minus ICRC minus IE RE. Okay. Keeping VCC here, VC goes that side and VE also goes that side. That's why the VC and IE are VE are both becoming minus now, and VCC remains the positive as it is. Okay, we are just writing this side and that, all the three expressions that side. Okay, and we also know that IC is approximately equal to what? IP. Now substituting there, what we are going to get now? VCE is equal to VCC minus IC common. Here we are substituting in terms of, this is RC. In terms of, in place of IE, if we take IC, we can take IC common. Okay. Minus IC into RC plus RE. Okay, this is the expression for VCE. So we got the expression for IC and VCE, where IC is V2 minus VDE by RE, where V2 is VCC into R2 by R1 plus R2. Okay. We have the we know how to calculate the value of V2. We know the RE will be present in the circuit, but what about VBE? VBE is a constant value. VBE is equal to 0.3, 0.7 for germanium and silicon. So VB are constant values for the type of transistor. If the transistor is a silicon type of transistor, the value of VB will be 0.7, of course, volts. If the transistor is a germanium type, then you will have to use 0.3 volts as VB. Okay. So these are the values for VB. So we have the expression for VCE now, and also the expression for IC, where all the different parameters are given here. In this expression, VCC will be given in the circuit, IC will we will be calculating here, and RC and RE are the part of the circuit. Okay. Now, this is the circuit analysis. Otherwise, finding the value of IC and VCE for a voltage divider bias circuit. Up to here, we are done. Now we have to find the end points. End points of load line, otherwise DC load line. Okay, DC load line, end points of the DC load line. For that, we will be using this expression. We are using that particular expression. Now we'll find the end points of the load line. That means IC, SAT and VCE cutoff point. We have 2 points now, right? So how to find the IC SAT? For IC SAT, in this expression, we put VCE is equal to 0. If we put VC is equal to 0, what happens? VCC comes this side. Otherwise, this term is already in positive. We will take IC this side. Both will become positive. So IC is equal to VCC by RE plus RC. This is the end point. Okay. I will write it again. End points of the DC load line. Okay, so what we do? Put PCE is equal to 0 where in this expression. So IC can be written as IC is equal to VCC by RC plus RE. This is the what? IC saturation point, the end point of the DC load line. For the other end point of the DC load line, what we require here? Now what we require? We put IC is equal to 0. We put IC is equal to 0. So what happens? The entire term IC into RC plus RE will be disappearing from the expression. So what we are going to get directly is VCE cutoff value is equal to VCC. So as you can observe, it is the same as that of the cutoff value of VCE for a normal CE configuration of a transistor. What changes here is the value of IC, where it was VCC by RC. One additional resistor is appearing here, that is called as the RE for this particular voltage divider bias circuit. Right? So these are the two endpoints, VCE cutoff and IC sat for the DC load line for a voltage divider bias circuit. Right? I will draw the DC load line for a voltage divider bias circuit. After drawing the DC load line, we will find the coordinates of the Q point, that means ICQ and VCEQ. So this is the expression for VC cutoff, that is VCC, and IC saturation endpoint VCC by RC plus RE, that we have found from the expression for VC is equal to VCC minus IC into RC plus RE. From this expression, we have found the two endpoints of the load line. So I am drawing the load line now on the output characteristics of a voltage divider bias circuit, where it is IC in milliamperes and here it is VCE in terms of volts. The endpoint IC sat is given by VCC by RC plus RE, whereas here it is VCE cutoff is equal to VCC. Okay, the two points are joined to form the load line. Okay. Now we know the expression for IC and IC sat. You know what is IC? Now the coordinates of the Q point. So what is the expression for IC? We have derived IC is equal to V2 minus VBE by RE, where V2 is equal to VCC into R2 by R1 plus R2, right? And VBE is equal to 0.3 and 0.7 for germanium and silicon respectively. Okay? And we also know the expression for VCE. So this is the expression for VCE ICQ. The same expression is used for ICQ. Whereas VCEQ is VCC minus ICQ into RE plus RC. This is the Q point coordinates, right? The Q point is given by VCEQ, comma ICQ. Okay. So these are the coordinates of Q point. You can get the Q point anywhere. We imagine it to be at the center. So this can be written as Q VCEQ, comma ICQ. Okay. So this is about the coordinates of the Q point. So we have analyzed the circuit of voltage divider bias. We have seen what is voltage divider bias, the circuit we have seen. We derived the expression for IC, which we can see here, and also what is V2 here and what is VB we know now. And we also derived the expression for VC for voltage divided by circuit, and from that we also found the two endpoints of the load line, and after that we also found the Q point coordinates of the Q point of the coordinates of the Q point for the voltage divider bias circuit, right? So by doing all this, we have not at all come across the term beta, right? In the normal CE configuration, starting in the beginning of this class itself, we had solved one problem where IC was beta into IB. Okay, so that configuration is depending on the value of beta, and beta is a constant value for what we can see different transistors. Depending on the transistor, the value of beta keeps changing. So here we can observe that this particular bias, that is voltage divider bias, when we are going to analyze the circuit, we came across some point that it is independent of beta. This particular what you can see biasing circuit, that means the voltage divider bias circuit, is independent of the beta. So you might be asked a question for 1 marks. Name the beta independent biasing circuit. So what is the answer? The answer will be voltage divider bias. So you have to remember that voltage divider bias is beta independent. Beta independent. It is very important point. Voltage divider bias is beta independent. Question will be, name the beta independent biasing circuit. So what will be the answer? Voltage divider bias. Okay. So this is the first observation we have seen here. It can be also termed as the advantage for the voltage divider bias circuit. So it is also the advantage. So as we are discussing the advantage, I will quickly write another advantage, that voltage divider bias is stable against temperature variations. So it can also handle the variations in the temperature. So the operation will be not affected due to the changes in the temperature. The operation of the voltage divider by circuit is also not going to be affected by the value of beta. So what does that mean? That basically means that in the circuit when you have designed, and if in future if you want to replace the transistor in that circuit, you can freely do that, because variation in the transistor is not going to affect the operation of the that particular circuit. Okay, so if you have connected a voltage divider bias circuit on your breadboard, and if the transistor is not working, otherwise if it has damage during the working, you can simply replace it by another transistor. That you can do because it is beta independent. Okay, so of course the similar type of transistor, because it is again depending on the value of VB also. So if instead of silicon type of transistor, you cannot use a germanium type of transistor. Different the other silicon type of transistor can be used, right? So about the disadvantages, what disadvantage we can see here is, of course, more number of resistors are there compared to a normal configuration where it used only 2, it is using 4. So as it is using more number of resistors, the calculation or the analysis of the circuit becomes little complex. Okay, the calculations become quite lengthy and complicated. That are the two disadvantages of the voltage divider bias. So about the voltage divider bias, we can see that it is independent of the beta. That means nothing that we can easily change the transistor used in the circuit. The similar type of transistor can be used. Okay. So this is the importance of the voltage divider bias. Advantage is it is beta independent and it is having better stability against temperature also. And these are the reasons for which the voltage divider bias circuit is widely used. In the beginning of the class itself, I told that voltage divider bias is most widely used type of transistor biasing, and these are the reasons. That means independent of beta is the reason for the voltage divider bias circuit for being widely used. Okay. So this is about the voltage divider bias. We'll be solving few numericals for this now. Numericals for the voltage divider bias. So I'm taking few examples for the numericals now. So they are giving a circuit with a voltage divider bias having values. I will draw the circuit now. The value of VCC 12 volts, 2K and 1K being RC and RA, plus 12 volts, 2K and 1 kilo ohm of course, This side R1 is 10 and this is 1K. Okay. This is 1K. Now what they are asking? Find the endpoints of the load line. Find the endpoints of the load line. So endpoints are IC SAT is equal to VCC by RC plus RE. 12 volts divided by 2K plus 1K, that is 12 by 3 is equal to 4 milliamperes. Why milli? Because denominator is having K. If it shifts to the numerator, that will become 4K. So IC saturation is equal to 4 milliamperes. Okay. VCE cutoff. They are asking the two endpoints, and the two endpoints are given by IC sat and VCE cutoff. Now, what is the expression? VCC minus IC into RC plus RE. 12 minus 4 milli into 3K. Oh, sorry. 3 volts, and this is 4 milliamperes. So 12 volts. IC is 4 milliamperes. Oh, sorry. This is just VCC. IC, we have put IC is equal to 0, right? So I have written the wrong expression here. The expression is directly cutoff value is, of course, when we put the VCC in this expression, when we are going to put IC is equal to 0, only then we are going to get the cutoff point. So it is directly equal to VCC, that is nothing but 12 volts. Okay. So we have the two endpoints now, VCE cutoff. The two endpoints are 12 and 4. So if we are going to draw the DC load line here, we are taking the voltage in the steps of 2, 2, 4, 6, 8, 10 and 12 volts. VCE in terms of volts, IC milliamperes. Okay, here we are taking again in the steps of 2, larger steps, 2, 4, 6 in terms of milli. So this is the 4 milli and this is 12 volts. This is the DC load line. That is joining the two endpoints, 4 milliampere IC SAT and 12 volts VCE cutoff. Okay. So this is the solution for this given question. Voltage divider bias is given. They are asking the two endpoints. The two endpoints are given by VCC by RC plus RE for IC SAT, and VCE is equal to directly equal to VCC. That gives you 12 volts. So the 2 points are 12 volts and 4 milliampere, and this is the resulting Q point. Okay, resulting load line. Now what they are asking, find the Q point for the circuit, the same circuit considering the transistor to be a silicon transistor. Okay. Now we require the Q point. Now they are asking the Q point. So we require ICQ given by V2 minus VB. They are saying it is a silicon transistor, silicon type of transistor. by RE. So first we will find the value of V2 now. V2 is equal to VCC by R1 plus R2 into R2. So 12 volts into 1K by 11K. That means 10 plus 1, 11K. So it will be 12 by 11. So what we are going to get the value as 12 by 11. 1.09 volts. So now this 1.09 volts is substituted here. This is a silicon type. So 0.7 divided by 1K. That means the value will be in terms of milliamperes. 0.9, 1.09, 1.09 minus 0.7, 0.39. Okay, the answer is 0.39, which can be written as milliamperes. Okay, so you can also write it as 0.4. This is ICQ, right? VCEQ, VCC minus ICQ into RC plus RE. 12 minus 0.39 into DT. This is milli and K gets cancelled. This is milli and this is K. So now 0.39 into 3, 1.17. 12 minus 1.17. 12 minus 1.17 will be 12 minus 1.17. 10.83. 10.83 volts. So the Q point is given by Q, the 2 points, 10.83, otherwise 10.8 volts, comma 0.39 milliampere. Okay, 10.8 will be approximately here and 0.39. So somewhere here the Q point will appear on the DC load line. Okay. So these are the two numericals that are asked here, where we found the first in with the same circuit. They asked the two endpoints. The two endpoints we found by the expression IC sat is equal to VCC by RC RE, and VCE is equal to VCC. We got the two endpoints. We draw the DC load line. Then they are asking for silicon transistor. If there is a silicon transistor, what will be the Q point resulting? So we found the two coordinates. For the coordinates, we found the value for V2. Substituting the value for V2 here, we got the expression for ICQ, which is 0.39. Again in the VCEQ, we substitute the value for 0.39 and we found the value of VCEQ to be 10.83. We got the 2 points for the Q point for this particular circuit. So we have analyzed the voltage divider by circuit in today's class, where we found the expression for IC and VCE first, and from that we found the two endpoints. That means IC sat and VCE cutoff we found, and again we found the coordinates of the Q point, the ICQ and the VCEQ, and we solved few numericals on that. We have also seen the advantages and disadvantages and also the importance of the voltage divider bias. There is another numerical I would like to continue with the topic voltage divider bias and the further topics, and another problem I will be taking in the next class. Thank you, my dear students.